Welcome to Chapter 2 of the Introduction to Process-Informatics series. In this lecture, we will master essential data preprocessing skills that form the foundation of every process informatics project. You will learn time series manipulation with pandas, resampling and rolling statistics, handling missing values, detecting and treating outliers, and proper scaling techniques. These skills typically consume 60 to 70% of total project time, making them crucial for success. Process data is inherently time-based, making Pandas Data Time Index your essential tool. When you load process data, the first step is converting timestamps to data time format and setting them as the index. This unlocks powerful time-based operations. Slicing data by date ranges becomes intuitive with bracket notation. You can select all data from a specific month, filter to a single day, or extract precise time windows. Always verify time zone handling, especially when integrating data from multiple systems. Raw sensor data often comes at high frequency, such as 5-second intervals or faster, creating unnecessarily large datasets. Resampling reduces data volume while preserving important patterns. Downsampling aggregates high-frequency data to lower frequency using aggregation functions like mean, max, or sum. Upsampling goes the other direction, interpolating to higher frequency when needed. The aggregation function matters. Use mean for smooth signals, max for peak detection, or sum for cumulative quantities. Rolling statistics reveal patterns hidden in noisy raw data. A rolling mean, or moving average, smooths short-term fluctuations to show underlying trends. Rolling standard deviation is equally valuable. It measures local variability. Stable operation shows low rolling standard deviation, while upsets cause spikes. Process engineers use rolling statistics for stability monitoring, detecting gradual drift, and identifying regime changes. The window size choice depends on the time scale of phenomena you want to capture. Missing data is inevitable in real process environments. Understanding why values are missing determines how to handle them. MCAR, missing completely at random, occurs when a temporary sensor communication error drops values at random. MAR, missing at random, happens when missingness depends on other observed variables, like a sensor that tends to fail when the measured temperature runs high. MNAR, missing not at random, is most challenging. Values are missing because of their actual value, like concentration sensors failing at high values. Different missing data patterns call for different imputation strategies. Linear interpolation works well for smooth, continuous signals like temperature. Forward fill propagates the last known value forward, appropriate for step change signals like set points. Spline interpolation handles curved patterns better, but can overshoot at boundaries. K-nearest neighbor imputation leverages correlations between variables. Always visualize before and after imputation to verify. The method produces physically reasonable results. Outliers in process data may indicate sensor failures, data transmission errors, or genuine process upsets. The z-score method flags points more than 3 standard deviations from the mean, assuming normal distribution. The IQR method is more robust. Calculate the interquartile range and flag points beyond 1.5 interquartile ranges from the quartiles. Choose your method based on data distribution and be conservative. In process data, genuine upsets are often more interesting than random noise. Single variable outlier detection misses anomalies that only appear when considering multiple variables together. Isolation Forest excels at finding these multivariate outliers. The algorithm works by randomly partitioning the feature space. Outliers, being rare and different, get isolated quickly in few partitions, while normal points require many cuts to isolate. You set the contamination parameter to your expected outlier fraction. Isolation Forest handles high-dimensional data well, making it ideal for process monitoring. Machine learning algorithms require properly scaled features. Min-max scaling transforms values to the 0 to 1 range, preserving the distribution shape. Standard scaling centers on zero with unit variance, assuming normal distribution. Robust scaling uses the median and the interquartile range, making it less sensitive to outliers. The critical rule: fit the scaler only on training data, then transform both training and test data with those same parameters. Fitting on test data causes data leakage. Let us recap Chapter 2. Data preprocessing is where process informatics projects succeed or fail, consuming 60 to 70% of total effort. Master these skills: Pandas data time index for time series manipulation, resampling to match analysis needs, rolling statistics for pattern detection, understanding missing value types for appropriate imputation, outlier detection matching your data characteristics, and proper scaling with train test separation. In Chapter 3, we will explore process modeling fundamentals.